and I'm excited to welcome you to Transfer Learning Between Largely Different Distributions, our top event. So now, let me start from some announcements. So I will actually introduce our event first. So today we will have 3 talks by invited PhD students from the US on the topic in the machine. But it's also in this topic today. And the plan of this event started about a few months ago when I asked Ananya to give a talk for this event. And Ananya was kind enough to accept the invitation. And later on, we decided to invite Dimitris and also Shivani and they were also kind enough to accept our invitation. And how did we decide on this topic? After the ICM kindly took my supervisor and me, and we had some interesting conversations on this topic, and also regarding our works at ICML. And a few months later, I was recalling this discussion with Ananya. We had over emails, and it hit me that it's a great idea to keep and reboot this conversation in a right way. How event now the beginning of the continued relations. So, and here I would like to show my special thanks to Professor Sugiyama for allowing me to make this event one of the public events at RIKEN AIP, our National Research Institute. And I would also like to show my gratitude to Nakano-san, our assistant, who helped me a lot for making this happen. Now, let me move on to first, and Ananya is on the West Coast, and Dimitris is, and also Shivani are on the East Coast, and I'm here in Japan. So we are actually on different dates in different, largely different time zones. And it was a little challenge for us to figure out which time slot worked for us, and we found out it's never best for everyone. So we decided to take this one, but hopefully after the summertime is gone, we may have a little better time slot. But I hope this is working for you now. But the good news is we are going to make a recording of this event. So this will be fully recorded and will be publicly available afterwards. And here are a few announcements. So here's how to ask questions. We are going to use this questions site where you are going to be able to post anonymous questions. So I will send this link to the Zoom chat after this announcement. So you can, just click on this to get to this website. And keep in mind that the chat is disabled and also unmute is disabled. So you will not be able to send out messages, but you're going to be able to ask questions here. So please click on the link afterwards. And another important note, this event will be fully recorded. So please keep that in mind. And the video will be made publicly available. train and test distributions are different, or at least signal low confidence when they are not able to make accurate predictions. And Ananya, could you set up your share screen and start your talk now?
Thanks, Takashi, for the introduction, and thanks for inviting me to speak here. All right, let me share my screen. All right, I hope everyone can see this. So I'm Ananya, and I'll be presenting joint work with my advisors, Tengyu and Percy, on understanding self-training for gradual domain adaptation. So when ML models are deployed in the real world, data distributions shift over time, and this leads to a drop in performance. For example, self-driving car vision modules have to deal with changing weather conditions, for example, snow on the roads. Brain-machine interfaces have to deal with changing neural signals. Chemical sensor measurements drift over time due to sensor aging. To address this question, we consider the setting of gradual domain adaptation. So we're given labeled examples from a source domain and unlabeled examples from intermediate domains that shift gradually in distribution towards a target domain. And the goal is to get high accuracy on the target domain. So as an example, we have the portraits data set, which is images from 1905 to 1973 of high school seniors labeled by gender. And we have labeled examples from the first 10 years and unlabeled examples for many decades after. And the goal is to get high accuracy on the target domain images from many decades later. So if we train a model on only labeled examples from the source, we get 98% accuracy on held out examples from the source, but only 75% accuracy on target examples, target images from many decades later. We could do direct domain adaptation where we for example, we could self-train or do entropy minimization on images in the target domain. And this gets us a little bit better to about 77% accuracy. Or we could leverage the fact that these distributions are gradually shifting over time and do gradual self-training, which I'll describe in this work, and that gets us to 84%. The oracle accuracy, which uses many labeled examples from the target domain, gets 91%. So gradual self-training closes about half the gap between the source and the oracle. So what is gradual self-training? So in the source domain, we have labeled examples, and we just train a regular classifier to distinguish over here between the red squares and the blue triangles. The data distribution now shifts by a small amount, and we only have unlabeled data. But since the shift is small, the original classifier W0 is mostly correct. So we use W0 to pseudo-label or just produce labels for these unlabeled examples. And we pretend that these labels are correct. And we train a classifier shown in the green dashed line that separates these two. We now repeat this process over time, and our classifier adapts along with the data. So first, I'd like to briefly mention some prior work because we build on a lot of amazing work that's been done in the past. So there are many empirical papers on this setting, the general setting of gradual or continuous domain adaptation. But there's little understanding of when or why this structure helps us and or principled algorithms to help us in these settings. There's also a lot of work on self-training, and it's been shown that self-training can get us really strong empirical results, state-of-the-art results on ImageNet, on domain adaptation. But there's little understanding on when self-training works or why it works. There's also a rich literature on unsupervised domain adaptation. So most of the theory assumes that the source and target domain are pretty close. They cannot be distinguished, for example. You cannot train a classifier that discriminates between them well. In practice, most distributions in domain adaptation, the source and target are very, very different. For example, in high dimensional data sets in computer vision and natural language. So empirical papers combine several heuristics to try and work for larger shifts. Each method works on some data sets, but not others. So a big question is, can we come up with something principled? So for some of these methods, people often spend like months tuning the state-of-the-art model for a slightly new data set to get it to work. So our contributions are, we show that the gradual shift structure enables theoretical analysis and reliable algorithms when the shifts are very large between the source and target. We also gain some understanding about when gradual shifts help us. So we'll show a lot of cases where it does and some cases where it doesn't. And we will show how to do gradual self-training properly, both in theory and practice. So our goal is theory that leads to practical insights. And we'll start with theory in two settings. So in the first setting, the margin setting, we assume at each point in time that there exists some classifier that can classify most of the data correctly, and also with some margin or spacing. So that's a pretty standard assumption in learning theory. The next assumption we'll make here is that the shifts are small. So the shifts are less than the margin in Wasserstein infinity distance. We'll also assume that the models are Lipschitz, so they don't have to be linear. They can be nonlinear, but Lipschitz. For the sake of this talk, we'll visualize and think about linear models. So our setting allows for the optimal classifier to change over time. As the data shifts, the classifier is allowed to change. So the first thing to note in this setting is that if you don't do self-training, if you just use the source classifier, it can quickly become stale and get all the examples wrong as the distribution shifts. So here's an example, a very simple example. You start out by getting most of the examples correct. You can separate between the red squares and the blue triangles. The data shifts and it shifts gradually, but within a few time steps, you might get most of the examples wrong. At this point, doing self-training or entropy minimization won't really help you because you're getting most of the examples wrong. So all your pseudolabels are wrong. So we show that self-training does better. It gives you some control, gradual self-training does better. It gives you some control over the error. So in particular, it shows that the error at time t is bounded by some exponential function of t times the initial error plus some generalization term. So we'll get to better bounds later, but for a note here, it gives you some control, whereas the other methods don't give you any. And if the initial error is very, very small, then it allows you to maintain low error for at least some time steps, even if the distribution shifts very far away. So I'll give a brief proof sketch of this result, but if it goes too quickly, don't worry about it. You can still understand the rest of the talk. So we start out with labeled data from the source domain, and we learn a classifier that separates between the red squares and the blue triangles with margin. And now the distribution shifts. The shift is gradual, so we get most of the examples correct with our original classifier at W0, but we only have unlabeled data. So we don't know the labels of these new examples. Now, we know that there exists some W star that classifies most of the data correctly with margin. We don't know what W star is, but for the sake of the proof, we know it exists. Now, W star does well on the original label, on the true labels, the ground truth labels, it gets low loss. But we don't have access to the ground truth labels. We have unlabeled data, and we pseudo-label them using W0. So in particular, the 2 points I've circled have wrong pseudo-labels. The pseudo-labels and the true labels are different. So what we want to say is that W star has low loss even for the pseudo-labeled data. And we'll use a key fact here. So this is a pretty key technical assumption, is that a pretty core part of the technical contribution is that you need a robust loss for this. So your loss needs to be upper bounded, for example, the ramp loss. So if you have a loss like the hinge loss, then it wouldn't quite work here. And the point is that for losses that are not robust or not upper bounded, even if a couple of the points change labels, the loss can change by a very, very large amount. But we handle these technical details. And the point is that W star is still good for the pseudolabeled data. It has low loss. So in self-training, we pseudo-labeled the unlabeled data, and we minimize the loss on the pseudo-labeled data. So we know that on the pseudo-labeled data, our classifier W hat is better than W star. It is not on the ground truth labels, where W star is obviously the best, but on the pseudo-labeled data, W hat is better. And W star was good on the pseudo-labeled data. So this means that W hat is good on the pseudo-labeled data. And finally, we note that the pseudo-labels and the true labels are pretty close. So this means that the classifier we got is pretty good on the true labels as well. So that gives us our bound that we get some control of the error when we apply this over many time steps. And we show that this bound is actually tight for self-training in this setting. So you can't do better than exponential. But in practice, we want better than exponential bounds. So the good thing about the previous setting is we actually didn't make too many assumptions. The distributions can be really, really complicated. They don't have any parametric distributional form. And the models don't have to be linear. They can be Lipschitz. And you still are better than no adaptation or direct self-training, even when you have large shifts. But in practice, we want something better than exponential. And so what we show is that if you imbue more structure into the problem, then you can get better than exponential bounds. So the motivation for this is that real world distributions are not quite so adversarial as what we get for our lower bound. So for example, if you plot the margins of most distributions, so here it's for MNIST, but you can see similar things for like C for our other data sets, they form very nice, they form a very nice shape. So for example, in this figure, we're plotting the model's confidence on the x-axis, so the sign confidence, and the y-axis is the number of examples. And it looks very nicely separated, almost like a mixture of two Gaussians, a Gaussian for the negative examples and a Gaussian for the positive. So intuitively, if you start somewhere close to the middle, then and do self-training, the gradient kind of points in the right direction. It gets you towards a more accurate point. So this is just intuition, just to motivate the setting. And we analyze a very simple setting in this paper, where an idealized setting where we assume that Px given y is an isotropic Gaussian in high dimensions. And so each class distribution is a Gaussian. And if these distributions shift around, then we can show that if you do self-training, you can maintain the Bayes optimal classifier. So this would not be an exponential bound. It would be polynomial samples, and you can maintain a very good classifier as the data shifts. There's been a lot of follow-up work since then that shows that this works for even more general conditions. So for example, the paper by Ening and Collin shows that it's not just for Gaussians, for isotropic Gaussians, but arbitrary Gaussians, and gives polynomial finite sample guarantees on the unlabeled data. And then Collin's done work after that, which shows that these kind of results work even if you have much more complex distributions, non-Gaussian, and deep neural networks. So if we have more structure on the problem, then we can, then self-training can do extremely well. But in the worst case, it does okay, but it could be exponential. So our theory leads to practical insights. And the first insight we draw from the theory is the key importance of regularization. And this is, we'll show that regularization matters even if you had infinite data. So in supervised learning, you typically need regularization when you don't have enough data. So when you have a small data set or medium-sized data set, then you need regularization, so you generalize better. But in this context, you need regularization even if you have infinite data. And the point here is that regularization lets you learn a classifier that not just classifies the data correctly, but classifies it with some margin or with some buffer. So on the left, we have a linear classifier that's trained without any regularization. So it can get the data right. It learns some kind of separator, but it doesn't learn it with margin. There's no buffer between the classifier and the points. So if the data shifts a little bit, you might get most of the points wrong. But when you add regularization, you ensure that you're far away from the points. So it makes it more robust to these shifts. So if you shift a bit, you still get the examples correct. The second essential ingredient is label sharpening. So there are many ways you can pseudo-label the unlabeled examples. So on the left, we show what we do, which is hard pseudo-labeling. So given an unlabeled point, you either label it positive or negative. If it's on the right side of the classifier, it's positive or red. On the left side, it's negative or blue. Another thing that some people do is soft pseudo-labeling, where each point is pseudo-labeled based on its distance from the margin. So it could be partially positive and partially negative. For example, if you have a logistic regression classifier, you can pseudo-label points based on your estimated probability that it's positive. So soft pseudo-labeling usually doesn't work because, strict soft pseudo-labeling, for example, using logistic regression doesn't work because your model would be well specified. So you'd learn the exact same classifier again. Self-training wouldn't do anything. And hard pseudo-labeling or some kind of label sharpening to interpolate between these two would be necessary to change your classifier. So we show that these insights from the theory matter a lot in practice. So across our data sets, which I'll talk about in a second, we show that gradual self-training does much better with explicit regularization and hard pseudo-labels. So there's a subtlety here. So for supervised learning, neural networks trained with SGD don't actually need much explicit regularization to do well, to get high accuracy. There's a lot of implicit regularization from the SGD that allows it to do fine. But in our setting, we find out that explicit regularization by adding a lot of dropout or L2 regularization or batch norm is critical. For example, in the rotating MNIST data set, if either are missing, then you get 45% accuracy. But if you add explicit regularization and hard pseudo-labeling, you get 84% accuracy. And we also have experiments in our paper showing that regularization remains important as you increase the data set size. So it's not just because of finite samples. So when you implement gradual self-training with regularization, explicit regularization, and label sharpening, you get large improvements across these three data sets. So we have a synthetic data set, which is rotating MNIST, and we have two real data sets, the portraits data set I talked about earlier, and a UCI data set where you're trying to predict the forest cover type given a bunch of features. And on all these data sets, the blue bar represents the oracle target accuracy if you had lots of label data from the target domain. The orange bar is gradual self-training. The gray bar is if you self-train directly on the target. And the horizontal light orange bar at the bottom is the performance if you only train on labeled examples from the source. And we can see in all these cases, the gradual self-training closes over half the gap between target self-training and the oracle. In our paper, we also give some insights about when gradual self-training works and when it doesn't. So our theory, the theory in the margin setting requires that the shifts in distribution are small in Wasserstein distance. So here's an example of that intuitively. So in the rotating MNIST data set, the source data set has images, regular MNIST images rotated by 0 degrees. Then the next domain, we have new digits, but so not the same digits as 0 degrees, new digits rotated by 20 degrees. And the next domain, it's new digits rotated by 40, and then new digits rotated by 60. So the angles are gradually shifting from 0 degrees to 60 degrees. So in this case, all the images from one domain to the next domain, or most of them, are shifting by a small amount. It's just a small rotation. And gradual self-training works really well here. So another type of small shift is small shifts in KL divergence or TV distance. So here's an example of that. In the source domain, we could have all the images. So we could have regular MNIST images. In the next domain, 1/3 of the images are rotated by 60 degrees. The other 2/3 are unrotated. The next domain, 2/3 of the images are rotated by 60, 1/3 are unrotated. And in the final domain, all images are rotated by 60. So in this case, the KL divergence or the TV distance between successive domains is small, but somehow it's not a very continuous transformation. And here gradual self-training doesn't help at all. So the point is that we need most of the points to shift by a small amount at each step. It's not just enough for like a small number of points to shift, but they shift by a large amount, even though that shift could be gradual in some metrics. So it's important to have some kind of continuity here. So I think there's a lot of scope for future work. So within this gradual domain adaptation setting, we've sketched out initial principled algorithms and theory in a couple of settings. But I think there's scope for better algorithms and more general theory, and also other application domains. More generally, we're interested in this question of domain adaptation for structured shifts. So can we leverage structure in the shifts to allow us to adapt to very different distributions where the supports of the source and target are very different, and you can easily discriminate or distinguish between the source and target domains? We've shown one example of this in our paper, which is gradual shifts. It's a pretty realistic structure, and it gives us a lot of leverage in theory and practice. And one question we're interested in is, can you discover these gradually shifting domains if you aren't given them? So some examples where this might be possible, you might have data with spatial information or other kinds of metadata. So right now we're looking at some data sets on crop prediction, poverty prediction, land cover prediction across the world. So you might have some metadata on location and other attributes which you can use to construct these gradual shifts. Or more generally, just given any kind of more general domain adaptation task, for example, predicting sentiment analysis and on Amazon reviews, where you have lots of different categories, you could discover a sequence of gradually shifting domains and then apply gradual self-training. I'd like to thank a lot of people for very insightful discussions and suggestions. And that's it for the talk.
Thank you, Ananya. I think there are 2 questions as of now that are on the Slido website. Can you see them?
Cool. Yeah, let me pull them out. Cool. So I think the first question is whether the Gaussian results can be easily extended to class-conditional distributions of bounded supports. So I think the answer to that is the Gaussian results can definitely be extended. And I think, for example, if you're interested in like more general stuff, it might be worth looking at a more, so this is a more general analysis on self-training, but also applies here. So there's recent work by Colin and his collaborators in Tengyu, which shows under an expansion property that self-training can work very well. And so it can address more general distributions. It's not, I don't think it's enough for it to just be bounded, but like this work will allow like multimodal distributions that have certain properties. I don't know if there's a way to figure out if it answers the question or not.
That's a good question. I think if there are any follow-up questions, please do write that in the slide.
Oh yeah, yeah, that's a good. Yeah. So feel free to ping again if I didn't answer. Cool. Another question was about the label sharpening strategy that is used. Do you have a hyperparameter for it? That's a great question, and I think there's lots of good work that can be done on exactly how you should label sharpen. In our case, we just compare kind of complete label sharpening, where you pseudolabel everything 1 or 0, or you do and fully soft pseudolabeling and hard pseudolabeling works better in theory and practice, but something in between could be the best. So I think that's a good thing to explore for future work. Cool. There's another question on, do we have a theory to deal with forgetting old data? That's a great question. So I think this is getting at like the continual learning or catastrophic forgetting kind of settings. So in our case, we assume you just have all the data. You can keep all the data with you, and you can keep self-training on them, or so you still have the labeled data from the source, which you can train on. You have all the unlabeled data since then, so you can just keep self-training. So we don't really address this issue, or I guess you can just deal with forgetting of old data. You can just go back and self-train on the old data. I think it's a great question to explore. Like, what if you just have tons and tons of data, or it's coming in a streaming setting? How do you prevent forgetting the old data? That's, I think, a great question to look into in the setting. We don't address that.
Great questions. I think even afterwards this talk on the admin webpage for Ananya, you can also see these questions, and also you can write the replies in text form. So even after this talk, we may be able to answer your questions. Oh, I think there's a
there's a follow-up question. So any difference between including the old data versus not including the data, performance changes in the rotation case? So I think my understanding of the question is, like, in the self-training phase, like, should you self-train on all the data that's come so far, or should you just choose maybe a more recent window of the data and self-train on that? So those maybe are the two scenarios to compare. So should you use all the unlabeled data and self-train on that, or the more recent one? So it turns out actually in the portraits data set, I did run some of these experiments, and it's usually better to focus on the more recent ones. But I think it depends what your objective is. So are you testing, is your goal to do well on all the data or just the more recent data? So in our case, our goal is to do well on the current data. So we're adapting over time, and at any point in time, we're testing on the current data. And in that case, it's often better to not self-train on all the data. So I have some experiments on that. It's better to self-train on a more recent batch of data. But if you're looking at performance on everything overall, you want a robust classifier that can work across all time periods, then I think it's an open question. You might forget some of the previous data. There's another question about, in the example of changing appearance of the road because of snow, to what extent can gradual domain adaptation cope with? And is there a way to measure it? So I think the best way would be to actually run on some of these data sets. So I didn't have a good data set. If you know of some data sets, please email me, and I'm happy to try. I couldn't find any good public ones available for weather changes or snow or things over time. And I think the best way is to just empirically try it. I think my general intuition is that the nature of the shift should be somewhat similar to the portraits kind of data set, or forest crop cover type data sets. So there's a reasonable shot it can change. And also, if you think about snow, I guess on an average, it comes up fairly gradually. So usually you have light snow towards the beginning of winter and then more heavy snow later on. But you might have to add more tricks because it's not completely gradual. You might, sometimes there might just be a sudden downpour of snow and everything might get white all of a sudden. So maybe what you really want to do here is you might want to learn how you're doing this gradual shift. You may not want to just shift over time. You might want to maybe use your neural network to find which examples are closer to the source. So for example, you can use the confidence of the neural network to figure out which things are closer, gradual self-train on those, and then expand to more and more different examples where it's snowing more heavily. So there might be more techniques you need to add on to make it work.
Great. Thank you so much for the many interesting questions, and thank you, Ananya. I think we are now going to move on to the next talk.
Great, thanks a lot.
Dimitris. Thank you. And let me share my screen again. Okay, sorry for the interruption, Dimitris. So let me briefly introduce Dimitris. He's a PhD student at MIT, advised by Alexander Madry, and his overarching goal of his research is to build tools for reliably deploying machine learning systems in the real world. And also, let me also introduce Shivani, who is a co-author of this the paper Dimitris' talk is based on. MIT, caused by Alexander Madry and Sharpen, and of models in the real world. So today's talk will be by Dimitris. Oh, can you, sorry, maybe there's a bad connection, but today's talk will be by Dimitris, and I probably Shivani will be also able to take these the questions in the Q&A sessions. So Dimitris, whenever you're ready.
Yeah, thank you, Daikashi, for the introduction and for organizing this event. I assume everyone can see my screen. Okay, so hi, I'm Dimitris, and I'm going to talk to you today about work on Subpopulation Shift. So this is joint work with Shibani, my fellow grad student at MIT, who's also here, and our advisor, Alexander. So in some sense, the entire point of this event is looking at machine learning beyond the test set. So if you look at the standard machine learning textbook, you learn that there is a data set, and we split this data set into a training set that we train our models on, and a test set where we actually test the performance of our model. And this makes sense. This ensures that whatever performance your model is getting, it is not getting it by just memorizing specific examples. But this is a very specific type of generalization. In some sense, this is the most basic science check you could do. Like, is my model just generalizing because it memorizes specific examples? In reality, you take your model and you deploy it in the real world. And the real world can be a very scary place for a machine learning model. There are many things that could be very different from the data you trained your model on. Equipment could be different. The things you try to recognize could change over time. So the question becomes, how can we actually build models that are robust and reliable enough so that we can deploy them in the real world? And today we're going to look at one facet of this question, what we'll call subpopulation shift. And the toy example to think about throughout this talk is we're trying to learn to classify dogs from parrots by looking at images of beagles and cockatoos. And these are training data that we use to learn a classifier between them. But then during testing, what we're going to see is we're going to see golden retrievers and macaws. And the question is, does our classifier actually learn to generalize to these unseen data subpopulations? And the dog versus bird setting is a very nice illustrative setting to think about this question, but you can think of very reasonable ways of extending this question into things like self-driving cars with different car makes or different equipments in a medical data set. So how can we evaluate our models on this axis? One approach would be to take a very large data set of dogs and separate these into the different dog breeds and do a version of the experiment we talked about. But this would basically require you to annotate the dataset from scratch because you would need to collect these population annotations. So what we're going to do instead is we're going to try and group together similar classes into superclasses. So what this pictorial looks like is you can imagine your dataset as having these basic classes, and these naturally fit into a hierarchy of concepts. For instance, all the dogs are mammals, all the birds are birds, and both of these are animals as opposed to object. So what we can do is we can actually define a new task that instead of classifying between these actual species, we can ask for a model to classify between these superclasses. And once we have this super task of like mammal versus bird, we can say that during training, some of these classes will be in the source domain, which is what we'll use for training, and some of them will be used for testing, which will be what we call the target domain. So this is what we call the bridge methodology. And this is the schematic you need to keep in mind. It's very simple. First, you choose a level of hierarchy. Then you define a classification task based on the superclass at this level of the hierarchy. And then you assign some of your subclasses, some of the original dataset classes to training. This is what in domain adaptation you would call source domain. And then you test your model on the unseen classes. This will be the target domain. And one of the nice things about this framework is that the part one is actually quite flexible. By choosing, for instance, different levels of the hierarchy, you can say that, oh, my shift can be more or less severe. So let's try to apply this methodology and create a few benchmarks. And the nice thing here is that we can actually reuse existing large-scale datasets. For instance, a very nice candidate would be ImageNet. It contains 1,000 diverse classes and actually has a hierarchy of itself. It has the WordNet hierarchy that every class is part of. But if you take a closer look at the WordNet hierarchy, you will see a few things. And we're actually surprised to see many of these things that make it like really tricky to use this data set for superclass prediction. For instance, we have things like cycles. For instance, bread is both in starches and in baked goods. So if you have starches and baked goods as superclasses, you cannot have bread as a class in your data set. Then we have things like abstract groupings. For instance, both roof and umbrella are coverings, but if we create a covering superclass, there's no way to learn that a roof is a covering by just looking at pictures of umbrellas. And then we have things like the granularity of these classes is very uneven. For instance, on level 3 of the original hierarchy, we have both street sign and living things, which are completely different in terms of the difference between what they contain. And at the core of these issues is that WordNet is not actually a hierarchy built for visual classification. It is just a hierarchy of words. So it's actually something that people did back then based just on the meaning of these words. So it does make sense in the end that it's not something that would make sense from a visual point of view. So what we actually had to do, we had to go in and modify this hierarchy, move things around, delete some nodes and so on, based on two. So first, we made sure that things are grouped only based on how they look. So we don't have any of these coverings, including both roofs and umbrellas. And then we made sure that everything that was at the level of the hierarchy is roughly the same granularity. So the way we did this is we got rid of nodes that were too abstract, for instance, categorizations that were unnecessarily specific. And then we also manually pushed some nodes down the hierarchy to match other nodes at that level. And it took some time, but actually got what we believe, and actually our human studies confirm, is a hierarchy that is much better calibrated for visual recognition. So with this hierarchy in place, we can actually go in and pick a bunch of different levels of this hierarchy and a bunch of different parts of it and create benchmarks. So these are 2 of the 4 benchmarks that we create. This is entity 13. It means that it has 13 classes from the entire ImageNet. For instance, you see it has birds, accessories, furniture, and products as its classes. And on the top row are examples of source images, and on the bottom row are examples of target images. And the same thing for living 17. This is a 17 class data set that has only living things. So cat, dog, ape, bear, and so on. So what we can take a look at first is, okay, how well do our models generalize? We created these benchmarks, and now we want to try and understand model behavior. So here is the plot. What we're going to look at is we're going to look at a bunch of different architectures. This AlexNet, VGG, ResNet, and DenseNet. And we're going to look at their source accuracy. And then we're going to plot the accuracy based on different testers. So the first thing to look at is the black dashed line is source accuracy, and the orange line is the target accuracy. And this tells you that because there's quite a big gap between these 2 numbers, it tells you that our models do not generalize as well as we hope for. The accuracy that they have on distinguishing birds from cats on the source domain is quite different from their accuracy in distinguishing them on the target domain. Then we can look at the multiplicative baseline. So this tells us that, okay, if all of our models lost a fraction of their accuracy, and we measure that fraction based on AlexNet, this is the first point, sorry, then how well do models perform? And what we see here is that because the orange line is higher than the gray line, it tells us that more accurate models are actually more robust to subpopulation shift. That is, the better targeted accuracy of more recent models is not just explained by their source accuracy. And finally, we can look at what happens when we retrain this model on the target domain. Whether this is retraining only the last layer, which is the green line, or retraining the entire network, which is the blue line. And what we see is that, okay, the last layer, we get quite a bit of performance boost, but not everything. And of course, by retraining the full model, we get something that is comparable to the dashed line, source accuracy, which makes sense because the target domain is not inherently harder than the source domain. After all, we just created them by splitting the dataset classes into two halves. So because we pick classes randomly, there's no reason to expect that one domain will be harder than the other. So now you may ask, okay, the performance of our model drops, but how big is this drop actually? Are humans equally sensitive to these subpopulation shifts? And to try and take a look at this question, we actually did a human study. And we presented annotators with the following task. So what we did is we showed them two groups of images, where every group is coming from a superclass in the source domain. So we picked two random superclasses, and then group one contains random source images from one of them, and group two contains random source images from the other. And then we showed the annotators a new set of images that contain random images from the target domains of these two classes. And what we want to ask them is, for each of the test images, do they belong in group one or group two? And so you can see here, for instance, that 6 of these images are turtles, so they're similar to group one, whereas the other image contains dogs, which is more similar to group two. And note that we actually don't tell them what are the names of these classes to avoid revealing by telling them that, group one is turtles and group two is dogs. So if you think about it, the accuracy of our annotators, how often they're actually able to put each image in the correct domain, is the same as asking them to perform a binary task of the same nature as we valued their models on. We're exactly training them, in a sense, by showing them images from group one and images from group two, and then we're testing them on the target domain and asking them to assign these new images to one of these two domains. Okay, so how well do humans perform? In order to understand this, we do the same experiment by also showing them test images from the source domain. And the blue lines are what our human annotators perform, and the orange lines are what our models do. The model, of course, we have to evaluate them on the same binary class. Essentially, we again pick random classes and we measure the binary accuracy of these models on this binary task between the source and target domain. And you can see a couple of things in these results. The first one is that, okay, models perform better than humans on the source domain. And this actually makes sense. Models have been trained on many more images and they're actually pretty good at classifying these images correctly. But then once you go to the target domain, the accuracy of the models is more often than not lower than what humans get on the target domain. And the important thing here is to see how much does the performance of a model drop when moving from the source to the target domain versus how much the performance of humans drops when we move from the source to the target domain. So it becomes clear that given, for instance, that like in most of these cases, humans actually perform better than models in the target domain and they have been trained on way fewer images. That's actually natural to assume that these benchmarks are actually well calibrated and humans don't suffer that much of a drop in performance. So then we went on to try and see if different robustness methods will allow us to perform better, to get models that are more robust to these subpopulation shifts. And the first question is, does training models on synthetic corruptions help? And here we're going to look at existing methods. For instance, adversarial training, where we train our model to be robust against small perturbations in L2 norm. We're going to look at erase noise that randomly erases patches of the image. We're going to look at Gaussian noise. And we're also going to look at stylized ImageNet, where essentially we pass each image through a style transfer pipeline to make the texture randomized. So this is focusing more on the shape of the image rather than the texture of the image. And what we're going to look at is, again, we're going to look at the source accuracy of different models. But because these robustness methods are actually causing models to have very often lower source accuracy, we will look at the relative accuracy on the target domain. So this is asking, what is the fraction of target accuracy to source accuracy? In a sense, this is telling us what fraction of their accuracy are models keeping when they move to the target domain. And what we can see here is that if you compare models to the blue circles, which are standard models, we see that both adversarial trained models and erase noise trained models offer improvements. So you can see, for instance, that in the entity 13 dataset, an adversarially trained model has higher relative accuracy, even though its original source accuracy is lower. And on the living 17 dataset, erase models are actually performing better than standard models, although in this case, the adversarially trained ones are actually performing worse. So the takeaway is that different robustness methods do help, do offer improvements, but these improvements are somewhat small. And then we can go on and ask, okay, what if we allow ourselves to retrain these models in the target domain by just retraining the last layer? Does pre-training on these synthetic corruptions help generalize? So here we're going to look at the same thing. We're going to look at models with different source accuracy. And then here, because we're not looking at different things, we're looking directly at, because we're training all of these models in the same way, we're fine-tuning on the exact same target dataset, we're just going to look at target accuracy. And what we see here is that the erase models are actually not any more better than standard models when it comes to fine-tuning, but the adversarially trained models are actually helping. And for instance, for the case of living 17, these adversarially trained models, after you fine-tune the last layer, are almost matching the original source accuracy. And this is interesting, and it actually agrees with some recent work that shows that from our lab and some folks at Berkeley, that shows that these adversarially trained models can actually adapt better to downstream tasks when you train them adversarially. So what are the takeaways? The most important one, in my opinion, is that we provide a suite of subpopulation shift benchmarks. I think that these benchmarks are quite useful. They are large scale compared to many of the other data sets that exist for these purposes. And they can be used to look at things like transfer learning, subpopulation shift, as we do in our work, or things like domain adaptation. Then we have a more visual ImageNet hierarchy. If you're doing anything that utilizes the WordNet hierarchy in any way, then moving over to our hierarchy is probably going to improve things. Makes more sense from a visual perspective. And more generally, I think that looking at the hierarchy directly, instead of just looking at classes as a flat set of 1,000 classes, will actually allow us to make some interesting progress on different aspects of model performance and model robustness. Yeah, what we saw is that standard models are actually brittle to subpopulation shift. Even if humans are not significantly affected by the subpopulation shift, models can actually suffer a significant drop in their accuracy. And if you look at the robustness methods that we currently have, they do offer some improvement, which shows promise that this problem is actually tractable, but current methods are not really offering any meaningful improvement. So it seems that there's still a lot of work to do in tackling these subpopulation shifts. So going forward, the big question is, how can we build subpopulation robust models? How can we build models that generalize better to new subpopulations? if this subpopulation shift exists and we cannot be fully robust to it, how can we at least adapt to it? How can we do good, efficient, and effective domain adaptation? And finally, this is only one side of the robustness question, subpopulation robustness. What about other notions of robustness? For instance, there's a lot of work at looking at things like input corruptions, fog or blur of noise, things like rotations and translations. But what are other type of, or for instance, Ananya was talking about time robustness. What are other notions of robustness that we should actually care about? So you can read more at our paper. We also have a blog post on this paper where we have nice visualizations of all the things I talked about. We also have a nice interactive demo of the hierarchy. And then you can access the hierarchy itself in the GitHub repo for a paper. So yeah, you can take questions now.
Thank you, Dimitris.
I see two questions.
Yeah.
Yes, measuring the human baselines. Yes. Yeah, so we crowdsource. So what we usually do our human annotations is we use Mechanical Turk, the Amazon Mechanical Turk platform, where you can essentially generate a task and post it there, and there are humans who will work on it. So we didn't ever meet these people. We just designed this web interface with these two groups and the checkboxes, and then we uploaded them on Mechanical Turk. We paid something like 15 cents per task, and yeah, and we got our data. Yeah, then the question is, have you explored the robustness of pre-trained models against the subpopulation shift? Shubhani, want to talk about that? You're muted.
Sure. Yeah, so far we haven't really explored the robustness of pre-trained models in this context, because usually these models are trained on all of ImageNet. But in our setup, we actually want to exclusively train the models on the subpopulations in the source domain and keep like certain subpopulations only for testing. So this is one thing that I'm not exactly sure how we could do that. But for our analysis, all the models that Dimitris talked about are standard models trained with like standard hyperparameter configurations and like architectures that people use. I think to actually be able to use pre-trained models, and this is something that there's like some work by Dan Hendricks, I think, where basically what they did is that they used ImageNet 10K, which has more classes than just the ImageNet that we usually think about, and they evaluated these pre-trained models on subpopulations that are in ImageNet 10K but not in ImageNet 1K. Unfortunately, I think that this data is no longer available for like the larger ImageNet dataset. But if there were to be some extension of ImageNet, then we can probably apply a similar methodology with pre-trained models to test on this data as well.
Yeah, so basically, the broader ImageNet dataset was taken down like a couple of years ago because many of the classes were like offensive and many of the images that they included, so, and hasn't been available since. So yeah, it would be actually great to do this thing for like existing models, but we could not. I did not understand if you have actually used your hierarchy of data to improve the subpopulation shift problem. No, so we actually did not use the hierarchy to improve the problem, in the sense that all of the models that we trained are just trained on the flat structure of the classes. We're still, like, the model never sees any hierarchy. The only thing we use the hierarchy for is to actually create the benchmarks to evaluate our models. And in some sense, the reason you care about the hierarchy being meaningful is because you don't want to measure completely arbitrary shifts, right? Like, if we use the original WordNet hierarchy, we would be training on umbrellas and trying to recognize them are roofs as coverings because umbrellas are coverings. So this is not a very reasonable way of creating a benchmark. But other than that, we do not actually give the hierarchy subpopulation, the hierarchy information to our models. But I think this would be something really interesting to try. Does this make sense?
Yeah, there's another question about how the use of the hierarchy seems to be a natural idea to perform some kind of gradual self-training. Yeah, this is definitely like an interesting idea and one that we did discuss with Ananya. Actually, Ananya also mentioned this, especially because it seems kind of an interpolation between our work and his work as well. So yeah, it could be something interesting to try, especially because like the hierarchy gives you a way to determine distances between subpopulations, but we haven't actually done this so far.
Yeah, it would make sense. Like you could start by self-training on nearby nodes and then start to look at classes further and further away from you. Yeah, and how did we decide to work on this idea? How? Mm. I guess we were thinking about like some, yeah, like distribution shift as a broad topic and asking ourselves like, what are reasonable benchmarks for distribution shift that we care about? And they seemed like one thing that was real world enough to care about and something that we could feasibly do without collecting a new huge data set because we already had the ImageNet data.
Yeah, I guess like two main considerations. One was that we wanted to explore like this area of distribution shift. And although there are like a lot of benchmarks in this space, the number of real world variations that like our models will encounter is much larger. And so our goal was to kind of look at some aspect of this problem that hadn't been looked at yet, and for which large scale benchmarks didn't really exist. And then, like Timur just mentioned, we wanted to find a way to simulate like realistic distribution shifts without really collecting data or like synthetically modeling these transformations. So like reusing the data set hierarchy and reusing existing data sets presented kind of like a nice opportunity.
Yes, we'll keep Stephen in mind if we make progress on this question. And the unanswered one is, yeah, if we tried things like self-supervised learning. So by self-supervised is nice. Oh, I mean, okay, things like pre-training, like contrastive learning or learning to predict rotations or things like that. No, we didn't try any of this. Like, I think it would be really interesting. I guess the point is that you would need to do it on a large unlabeled data set. So I guess it depends on what your model is. For instance, you could look at the domain, assume that you have a lot of data in the target domain, but there are no labels there. So you could self-training on both the source and target domain, and then use the label data from the source domain and see what's happening. I think this is like a very interesting research problem that we didn't have the time to look into yet. So what's the overlap between self-supervised and domain adaptation? And I would say they're quite different problems. Yeah, I guess a way to connect them is like say that, okay, like basically self-supervised means that you have a large set of unlabeled data and you're trying to, yeah, you have basically a large set of unlabeled data and you're trying to train your model without labels on some dummy task. For instance, you rotate images and you try to predict what the label of these images are. So your model is learning some representation that's useful. And then you can fine tune this model with a few labeled examples from the other domain. So I guess you could imagine something like self-supervised domain adaptation, which would be this methodology. In general, self-supervision refers to this general paradigm of you train your model on some task without labels. For instance, this could mean that from some part, like you remove some part of the image and you try to predict this image from the surrounding image and so on. And domain adaptation is the general problem of you have two domains, you train your model in one domain and you're trying to adapt it on the other. I hope this makes sense. So just to summarize, one of them is a methodology, the other one is a problem, and you could definitely use this methodology on this problem.
Okay, so I think that's the last question. And thank you so much,
Very nice.
Dimitris.
Yeah, thank you so much for organizing this. I can stop
you.
sharing.
Okay, so now let me continue to my presentation. So here's my little introduction. Kishima. Supervised by what I can do now is to speak a little slowly so that you can interpolate between sounds. So my name is Takeshi Teshima. I'm a PhD student at the University of Tokyo, supervised by Professor Sugiyama. I'm also a junior research associate at Riken my research we were able to make this event a little bit of a different type from the two talks earlier. But let me sorry. Let me start my presentation. So today I would like to talk about few-shot domain adaptation by causal mechanism transfer. Issue, it's probably catching some of my words. Please write in the slide so that I can explain that that part. But so today I'm going to talk about this work we presented at ICML 2020, and this is a joint work with Professor Issei Sato at the University of Tokyo, and also my advisor, Professor Masashi Sugiyama. Here is the overview of this work. The problem we are tackling here is domain adaptation, which is the entire topic of this event. And the central question in domain adaptation, of course, is when is it possible? What underlying assumptions could we use to enable domain adaptation? And we try to explore the possibility of using causal mechanisms, the similarity of causal mechanisms behind the data distribution to enable domain adaptation. A causal mechanism, which I will explain later, is an underlying generative model of the data. And we're trying to say that common causal mechanisms as the relations between different data distributions could be the basis or a foundation for domain adaptation. So what do we mean by causal models here? These are specific generative models of the joint distribution of data called structure equation models. So we're going to consider these generative models behind the data distributions. And a structural equation model, or SEM in short, consists of a pair of functions and also a distribution. The set of functions F are deterministic functions, which take as input some latent variables, as well as some of the observed variables, and they output the observed variables. So let's say we have 4 variables, 3 of which are the predictor variables, x1 to x3, and one of them is the predicted variable y, x1 to x3 and y are the outputs from deterministic functions, f1 prime to f4 prime, which take some of these x1s to some of these x's and y's as inputs, as well as some of these, as well as one latent variable for each of these functions. And the paired distribution Q is assumed to be an independent distribution of these latent variables. So what we are assuming here as a generative model is that the data that we observe are generated by this process, that each of these latent variables are sampled from this distribution Q, and then they are converted by applying these deterministic functions, f1 prime to f4 prime. And we assume that we have a so-called acyclicity here, so that we can actually perform this process. And we are going to use something called nonlinear ICA in order to perform domain adaptation later. So let me explain what it is here. We use so-called nonlinear ICA, but sorry, let me rephrase it. So the importance of nonlinear ICA here in relation to this work is that they can actually somehow solve these structure equations. So in the previous slide, we showed what structure equation models, SEMs, look like. And that's on the left-hand side. And this form, which takes the latent variables and some of the observed variables as inputs and outputs the observed variables. This form is called structure equation, structure form of the structure equations. And we solve these structure equations for the observed variables, which means that we sequentially input the variables to the right-hand side to express the observed variables in terms of, as a function of the latent variables, like on the right-hand side. And this form is called the reduced form. And what's important about nonlinear ICA is that when we have a reduced form equation, like on the right-hand side, there are, under certain identification conditions, there are ways to, nonlinear ICA provides a way to estimate this function f. So given that we have structure equation models like on the previous slide, nonlinear ICA provides us a way, a possibility to estimate this f on the right-hand side. And now let me move on to explaining the motivation of this transfer learning. Well, as we are all aware, data is a scarce resource, and we want to exploit as much information as possible. So that's when domain adaptation comes in. We want to use data from related but different different probability distributions. And of course, we need some assumptions to describe the relation of the source distribution that we learn from and the target distribution where we want to perform well in making predictions. So what commonality to exploit? And we're trying to answer this question by introducing causal, the idea of common causal mechanism behind data distributions. Why do we consider causal mechanisms in domain adaptation? The basic intuition is that humans care about finding causal knowledge because once they are discovered, this knowledge, in a sense, causal knowledge is important because they are portable. And one imaginary but motivating example is regional disease prediction. Let's say we want to predict disease risk from medical records. However, in the specific region that you want to make predictions in, you may have scarce data. So you may want to use data from other regions. But the difficulty is that the data distributions, here the distribution of the medical records and the medical history, the data distributions may differ from place to place because of different, for example, different lifestyles, different dietary habits, different exercising habits, etc., due to different cultures, etc. So the difficulty is that the data distributions on the surface may differ, but we may be able to exploit the fact that each of these data are generated from a common pathological mechanisms, which we may be able to safely assume to be the same because we are all humans. So let's say we are given some medical records as well as medical history from different regions. We may come to a point where we want to exploit such latent structure that's behind the data distributions, even if the data distributions themselves look different. So here's the formulation that that this talk will be based on. So as a basic setup, we will consider only the regression problem, domain adaptating regression problem. And here are some basic assumptions, basic problem setup we will consider. First, it's homogeneous, which means that all domains share the same variable spaces. The variables, the data taking the same set of values. And the second assumption is that we assume it's multi-source situation, which means that we have multiple source domains. So we have data from multiple source distributions, each of which are IID, and we assume that we have many of these data. And the third setup is that we will assume we are in a few-shot supervised situation, which means that we have data from the target distribution, but the data set size is small. So our goal is to make accurate predictions for this target domain distribution, but we are only given some small data from this target distribution. And we want to exploit the data from related but different source distributions. And I will explain what will be the relations, assumed relations between the target distribution and the source distributions. As a base assumption, we will assume that each of these domains follows a nonlinear ICA model, or it's essentially the same as assuming that there are structure equation models behind the data distributions. But as a slight generalization, we will simply just assume that each of the observed variables, let's say X and Y, are generated by first sampling the independent components from a hidden independent component distribution, Q. And second, they are converted by using a certain invertible function, F. And this converted random variables are what we are observing here. So we will assume that all of these target distribution and also the source distributions follow some kind of structure equation models of this form. And the key assumption advantage here is that we will assume that the function that was used to convert the independent variables into the observed variables, the function f, these are the same for all domains. So we assume that these f's are shared across all domains, but we will not assume that q's are the same. So these distributions of the latent variables, independent components, can be very different. I mean, they can be basically arbitrarily different, but we will assume that they are converted into the observed variables using the same function, same system of functions, f. So even though we assume that these functions, f's, are the same for all domains, including the source domains and the target domain, we will, since these latent independent component distributions can be flexibly different, the resulting distributions of the observed variables can be also largely different. Under this setup, here is the idea of how to exploit the assumption. As the first step, because f is the only thing that's assumed as the commonality between the domains, we will first estimate f using the source domain data, which is enabled by recently developed nonlinear ICA methods. And these f's were assumed to be invertible. And here in this estimation, we use so-called invertible neural networks so that we can actually estimate f, but at the same time estimate f inverse. And in the second step, after estimating f, we get the estimates of the independent components from the target domain data using the inverse of the estimated f. So by this step, we can get, we essentially extract the set of estimated independent components from the target data. And in the third step, we inflate this estimated independent components. So we get the what we call candidate independent components by exchanging the values, which I will explain in the next slide. And by performing this third step, we actually obtain an exponential number of, essentially all combinations of possible independent components that can be estimated from the target data. And in the fourth step, by performing this third step, we get many expanded independent component sets. So in the fourth step, we apply the estimated f again to each of these inflated independent components to get increased number of the pseudo target data. And in the last step, we fit a predictor to this generated pseudo target data. And what we mean by exchanging the values or getting the candidate independent components here is like this. Let's say we align the estimated independent components from S1 hat to Sn hat in a matrix form, where we have for each column, each estimated independent component sets correspond, and so each row here corresponds to each dimension of the independent component vectors. And what we mean by exchanging the values is that we take all possible combinations of the values from we take one value from each row, so that by selecting one column. But sorry, we select one value for each row by selecting the columns, and the combination of the columns can be arbitrary. So, and we take all possible combinations of these columns. And by taking one value from each row, we form a new unseen independent component set, independent component vector, like on the right-hand side. So we first estimate these S1 hat to Sn hat. We align them in the matrix form and take all possible combinations of the elements of the estimated independent components to generate essentially n power to d points of vectors. By doing this, we're exploiting the independence structure that's assumed on the distribution of the independent components. And by performing these 5 steps, we can inflate the target domain distribution data into n power to d new pseudo data points, and we can fit the your own predictor on them. So the question is, theoretically, how does this method possibly help? So the first, to answer this first question, we formulated this theorem in which explains how this helps statistically in an idealized situation. So let's say we have a perfect estimation of this underlying function f. That means f hat equals to f. In this case, the empirical risk estimator that's constructed by using the pseudo data, it becomes the uniformly minimum variance unbiased risk estimator. So in this idealized situation where we perfectly estimated the underlying f, by applying this method, we can get the target risk estimator of the minimum variance among all possible unbiased risk estimators. And this roughly says that the method should help, the proposed method should help in terms of variance. And the second question is, what happens when the estimation of f is not perfect? Because we estimate this f, in reality, this is more likely the case. And what's the catch in that situation? To answer this, we investigated the generalization error bound in the case of the f hat not equals to f case. And in this case, we can formulate this generalization error bound, which we can interpret as follows. So by inflating this data, because we increase the data points, we are able to fit more complex predictors with higher confidence. So essentially, by applying our method, by inflating the data using the hidden structure, we can mitigate overfitting. However, on the other hand, if these generated data are at some wrong places, then we are fitting these complex models in wrong places. So if the estimation of f is not perfect, because of that fact, we can be introducing some bias. So we are this. So in summary, theoretically, this method, we can interpret this method as a sort of a method to trade off between bias and overfitting. So we may be introducing bias in a non-idealized case, in a realistic case, but we are still increasing the number of points, which allows us to avoid the overfitting issue. And we did some experiments using some small real-world data from econometrics. So we used this gasoline consumption data set from a textbook of econometrics. And on this data, we selected this data because structure equation modeling have been applied to this data set over and over. And this using this data set, well, this is a panel data set, and we treated different countries in the data set as different domains. And we treated the, it's actually a time series data, but we destroyed this time series structure and considered each of these values for each year as a data point. And we compared the proposed method with some baselines using some using the Kanner ridge regression predictor. And this is the actual result, but this is for those who have really good eyesight. So for the actual figures, please check our paper. But the brief message that we can extract from this table is that the proposed method about half the time improves the performance of the baseline, which uses only the target domain data, even when the other methods using that can use source domain data suffer from negative transfer. So there are situations where there seem to be situations where the proposed method really helps, even when these other baseline methods, which is source domain data, cannot extract this commonality between the source data and the target domain data. So here's the conclusion part. The takeaway is that we investigated the possibility of using transfer assumption of shared generative mechanism behind the data distributions. We developed the first few-shot regression domain adaptation method for it. And the proposed method extracts and uses the causal model to reduce the overfitting via data augmentation. And we performed some experiments with real-world data to demonstrate the validity. So that's the end of my part. If there are any questions, I'm sorry, I probably had some connection issues and that wasn't very nice today, but thank you very much. If there are any questions, I guess I will wait for 1 or 2 minutes now, but does someone want to say something, or can I just move on to the conclusion?
There's a question.
Oh, thank you. Okay, did you try some other data sets which you're not sure whether SEM holds or not? A good question. For this work, I haven't done that, but I should. So, so the short answer is no, but I will do that. Okay, so I think, shall we move on to the conclusion? Okay, so let me see. Let me share my screen again. Okay, thank you. I'd like to thank every participant and also all of you, my fellow friends, speakers, for coming today. And we really appreciate your feedback. So what was your experience in this event, or what was interesting to you? Please write your feedback to the Slido that we were using for the Q&A sessions, this website. So if you could type in your feedback into this question form, we'll be able to check them later and take some stats, hopefully. So please feel free to, please do write your feedback on this, about this event in Slido. And that calls the end of the event today. Here's a little graphic, a remote one. And I'd like to thank everyone for joining. For follow-up questions, please use Slido. And I will announce the URL for the recording on Twitter and probably on the event registration site. So please check them out.
Thank you so much, Takeshi, for organizing this.
Oh.
It was a lot of fun.
Thank you so much.
Yes, thank you. And I guess you could also
thank you very much.
Feel free to reach out to us in general with questions.
Thank you. Oh, sorry, I couldn't catch your last part.
No, I just wanted to say that people should feel free to reach out to us via email with questions even after the event.
Thank you so much. So the personal web pages of us can be found on the event registration site. So please reach out to us from those links. Thank you very much, everyone, for joining.
Thank you.